Well, thanks for having me, Alicia. I'm going to present some things from Hugh Smithy's new chemical analyses of the granites collected by Cassidy and Champion, and I'm going to compare that to some of the analyses from specific mineralised districts, just to get an idea of what kind of magmas are linked in some way or other to gold systems in the Yilgarn. Now, I'll add a disclaimer at the start, and that is I don't know much about magmatic chemistry, but I do get to see lots and lots of databases. So I can see patterns in the data, and the patterns are real, but my interpretations might be a bit fanciful. So if you want to know what's really going on, ask Hugh Smithies. One of the things that's always fascinated me is that there are quite a number of porphyries in the Yilgarn that have consistent elevated gold contents, like this one, for example. So if we were to plot gold grades in the porphyries and in the adjacent country rocks as cumulative frequency plots like this, what we would see is that the ore bodies in the country rock will have a small percentage of the data that's plotting, 1, 5, 10 grams. But the granites that are sitting next to them are consistently mineralised, not necessarily with ore grades, but quite often with hundreds of metres of 0.1, 0.2, 0.3 ppm gold. So I'm particularly interested and fascinated by these intrusions. What is it about the chemistry of these intrusions and the way they were generated that makes them gold rich? Can we see that in the trace element chemistry? I'm going to make a quick comparison with porphyry copper systems. Most of the porphyry copper deposits in the world just have economic copper. There's a relatively small proportion of them have economic gold as well as copper. So think about the degree of enrichment between the source region where the melts are generated and the ore body. The average andesite has about 50 ppm copper, and average basalt has 100 ppm copper. Right? So if we go from the source region where the melts are generated into the porphyry ore, for copper, there's an enrichment of about 100 times. So the porphyry experts, people like Bob Laux, would say that you can take any old basaltic source, generate an andesitic magma under the right conditions of pressure, temperature, water content, right? So long as you fractionate it sufficiently, any old basaltic source region can generate a porphyry copper ore body. But the same is not true for gold. So the background gold is less than 1 ppb. It's probably less than half a ppb. So to get to an ore grade of half a gram, it needs an enrichment factor of 1,000 times. Right? So the fractionation processes that generate a porphyry copper deposit are not sufficient to generate a porphyry copper gold system. There has to be something different about the source region to generate a porphyry copper gold system. And the consensus of opinion amongst the porphyry experts is that the gold-bearing systems come from an enriched mantle source. And the enrichment process in the mantle involves sulfide saturation of a melt that's cooled and crystallized in the mantle and then been remelted. The important thing about sulfide saturation, like how do you generate gold enrichment in the mantle? When a melt becomes sulfide saturated, gold has a huge partition coefficient between the melt and the immiscible sulfide droplets. So as soon as there's an immiscible sulfide melt kicking around, it will sequester all of the gold from the melt into those sulfide grains. And if you have some kind of process that can remelt that material by replenishment of the magma chamber, for example, then that's potentially a mechanism for generating a really gold-rich magma. And that's the kind of hypothesis we're going to look at in the Yilgarn data. So we've got a few assumptions here that I'm going to consider. This is not an assumption. There is a spatial association between gold-bearing porphyries and orogenic gold systems. The topic that I talked about at the previous Raglan lecture I gave a couple of years ago, I gave some evidence to show that the orogenic vein systems were occurred within the footprint of hydrothermal alteration surrounding porphyries. So it looks like there's some kind of precursor alteration and enrichment in water, CO2, sulfur, and gold in alteration systems surrounding those intrusions. And then metamorphism of that altered rock is the process that creates the orogenic deposits. And then the real big assumption here is that these gold-rich porphyries acquire their metal from an enriched mantle source. And we think that's because of a pre-enrichment event in the mantle rather than fractionation within the magmas. So just to begin with, I'm going to look at that previous topic I spoke about the alteration systems around the intrusions and how they are a likely precursor to the orogenic gold systems. The absolute clearest example of this is Wallaby. So these are photos of some of the types of intrusions at Wallaby. The main one is this porphyritic syenite. So these are great big K feldspar phenocrysts in an albitic ground mass. There are finer grained intrusions like this one, cyanites. There's a bunch of things that are variously described as monzonites, and there's the occasional carbonatite with great big pyroxenes. And the alteration around the intrusions look like this. Close to the mineralised lodes, there's an intense albite dolomite alteration, so the rock is completely bleached. All of these slabs of core here are all Wallaby conglomerate. So these have got basalt clasts, they've got hornblende diorite clasts, it's got the occasional BIF clast and a few ultramafics in there. But around the orogenic lodes, we see this albite dolomite alteration. Outboard from that, there's biotite. So this black colour is pervasive biotite in the ground mass of the conglomerate. The most obvious alteration style is this material. This is a mineral assemblage of actinolite, magnetite, epidote, pyrite, calcite. And this is the alteration type that gives Wallaby its really distinctive magnetic bullseye. Sitting outboard of that and going for kilometres is chlorite, paragonite, calcite assemblage. So this is the same type of mineral assemblage that we see at the Golden Mile, for example, in the Paringa basalt outboard of the Golden Mile dolerite. These are some figures I lifted out of a paper by Brock Salia. So Brock did his PhD at Wallaby about 2000, the year 2000. And this was a Geochronology project. So this is Brock's cross-section of Wallaby. The black lines in here are the syenite suite. So these are the intrusions. And these are really elongate pencil-shaped intrusions. Right, so this includes the porphyritic cyanites, the monzonites, and the lamprifiers. The horizontal hatch in here is the outline of that magnetic actinolite magnetite epidote alteration. And the horizontal grey zones in here are the gold lodes with the albite dolomite alteration. And this is really important to note. All of the gold-bearing lodes in here, like the things that clearly look like orogenic veins, all sit within the footprint of this earlier alteration that is clearly forming an envelope around these intrusions. So we've got the same style of deformation, the same style of metamorphism throughout the greenstone belt, but the gold lodes only occur here, superimposed on top of this early alteration event. And you can go to any of the deposits around Laverton or anywhere around Kalgoorlie and you'll see the same spatial relationship. Probably nowhere else as clear as it is here. What we more commonly see perhaps is a vein array sitting outboard of the intrusions, but we always have this kind of spatial relationship between some kind of weird intrusion and the alteration halo surrounding it, and then the orogenic lodes. So Brock has got some age dates out of the intrusions, and he's got these with a variety of techniques, but he's dated titanite, and he's getting ages of about 2660 to 2664 with fairly good analytical precision. Right, so let's just put the age of the intrusions at 2662. The next thing he did was he went and looked very closely at the lodes. So here's a picture of one of these flat lodes underground, and it has stylolytic laminations near the margin, and it's got breccias internal to the vein. And within the vein, he has found monazite and xenotime grains that are in contact with quartz inside the quartz veins. And he's got pretty good age dates on those, and they come out about 15 million years younger than the intrusions. Right, so we see this really common association where we get intrusions around 2665 to 2660, and then orogenic veins dated at anywhere from 2630 to 2650, but always, nearly always, within the footprint of that earlier alteration. So that's kind of the background. I'm interested in characterizing the chemistry of the intrusions that are related to those gold systems. And I'm going to get into some heavy-duty chemistry here. So I'm going to give you a lightning-fast course on magmatic chemistry in 5 minutes. So all the igneous petrologists have got heaps of jargon when they talk about magmatic chemistry, and I'm going to explain just a few of those terms. So one of the things if we consider the suite of elements that we can analyse with 4-acid digest ICP-MS, right? We won't look at the whole periodic table, just the common analytical suite that you'll get from your routine commercial assays. There's a group of elements that we would refer to as high field strength elements. So out of the assay package that you would normally be looking at, these will include yttrium, zirconium, niobium, lanthanum, cerium, hafnium, tantalum, thorium, and uranium. These are all elements that have an ionic charge of +3 or +4 or +5 in the case of niobium and tantalum. So because they have a high charge, they have a really small ionic radius. And that means that they do not fit into common minerals. So these are elements that we would refer to as incompatible elements. So as a magma is cooling down and crystallizing, we'll be crystallizing out plagioclase and pyroxenes and amphiboles, and very little of these elements will fit into those common silicate minerals. So as the fractionation proceeds, the concentration of these elements in the remaining melt gets higher and higher and higher. That's what we mean by incompatible. And in the late stages of cooling, we'll start to see minerals like zircons, we'll see iron titanium oxides and phosphates. And they're the main minerals that will take up these elements. As another group of things that are referred to as large iron lithophile elements, and generally would be referring to rubidium and cesium and barium. So these are big cations with a charge of +1 or +2. And I'll put lithium in there as well. That's the opposite. That's a tiny, tiny little ion. So these are things that would like to substitute into common silicate minerals, but because of their very large or very small size, they don't easily fit into those minerals. And these will be the things that go into the last bit of feldspar or mica that crystallizes from the melt. Right, so all of these, rubidium, cesium, barium, all go into K feldspar. Lithium will substitute for magnesium into the last crystallized ferromagnesium minerals. The next thing, I'm going to briefly look at the first row transition metals. And titanium will go into oxides, chrome and nickel follow magnesium, but the rest of these in red all have chemistry that's very, very much like iron. So all of these things will be highly correlated with iron. So they'll go into pyroxenes and into hornblende and into biotite. But they all have some quirky little thing that makes them a bit different to their neighbours. So the way they partition from each other is really important in working out which mineral phases are crystallising and fractionating as a magma evolves. There's only one phase diagram in here. This is kind of important. What I'm going to discuss here mostly is the differences between magmas that are generated at high pressure versus those that are generated at low pressure. And that's because pressure and water content dramatically change the order of crystallization of common magmatic minerals. So that dramatically changes the trace element signature of those magmas. And it's important in what kind of mineral systems they eventually evolve to. This is a diagram from Bob Laux' famous porphyry copper paper, and this is a plot of temperature versus the concentration of water in the magma expressed as partial pressure of H2O. Now I really need to put in another diagram that shows temperature versus pressure, but it's kind of similar. So we'll just get by with one figure. The really important thing to note in this diagram is what the water content does to the crystallization temperature or the melting temperature of plagioclase. Right? At low water contents and at low pressure, plagioclase crystallizes at pretty high temperatures. As the water content goes up, or as the pressure increases or the depth gets greater, plagioclase crystallization happens much, much later on, so at much lower temperatures. And one of the things we'll see here in a minute is that at high pressure and at a high water content, there's a calcium mineral called titanite that crystallizes before plagioclase. The other really important thing on this diagram is the point curve of magnetite compared to hornblende. So once we get to high water contents and high pressures, hornblende crystallizes before magnetite. And we can see the signatures of those things in whole rock chemistry. So let's look at a few different fractionation indicators that igneous petrologists would look at. Now, I'm guessing that most of you will know about europium anomalies and how that relates to plagioclase fractionation. Just as a quick reminder, europium is a bit different to all of the other rare earth elements. All of the rare earth elements have a common valency of +3, but europium can also be +2. And europium 2+ substitutes for sodium into plagioclase. So as plagioclase fractionates, it will remove europium from the melt. And this europium anomaly number here is a measure of how much europium is depleted relative to the adjacent rare earths, relative to scandium and gadolinium. So if there is no depletion of europium, if there's no plagioclase fractionation, then this value would plot at 1. Right? So here I'm plotting the magnitude of the europium anomaly against silica. I'm comparing two different data sets here. The one on the left, these are rocks from the Mount Reed volcanics, and this is like a type example of mid-crustal melts. So these are the sorts of melt compositions and fractionation processes that we would see at low pressures. The plot on the right is from an Eocene porphyry belt in southern Peru. So this was written up and published in a PhD thesis 4 or 5 years ago by a French dude who's now professor in the University of Zurich. And what we can see by comparing these two plots is that the mid-crustal melts show a much more significant effect from plagioclase fractionation. So as the silica content goes up, the europium anomaly is getting deeper and deeper and deeper. One of the characteristics of porphyry copper magmas is they are high-pressure magmas, generated high pressure, so they don't have such a pronounced europium anomaly. Now we'll compare what happened to the high field strength elements. And just for the sake of simplicity, I'm only showing one of the high field strength elements. I'm just showing niobium. So niobium is typically an incompatible element. As silica goes up, the abundance of niobium gets higher and higher. And note the scale here goes from 0 to 20. This is what happens in porphyries. This scale goes from 0 to 5. Right? So in porphyry systems, the niobium initially goes up, reaches a maximum at about 60, 62% SiO2, and then it starts going down. And this is due to titanite. Titanite is calcium titanium silicate, and it's an absolute junk bag. So titanite takes up all of the niobium, all of the yttrium, all the thorium, all of the rare earths, light and heavy rare earths, and as titanite fractionates, all of those incompatible elements start behaving in a compatible manner, so they start being depleted out of the melt. A lot of the porphyry guys will plot a ratio of strontium over yttrium. So in low pressure magmas, plagioclase is fractionating and it's removing strontium, but yttrium remains incompatible. It stays in the melt. So the strontium-yttrium ratio goes down. That's what we'd see in a low pressure magma. This is what we see in a high pressure magma. They have high strontium because plagioclase is not fractionating, and they have low yttrium because titanite is fractionating and being removed from the magma. Right, so they go in opposite directions. Now we'll look at vanadium-scandium ratios. In low pressure magmas, magnetite crystallizes before hornblende, and vanadium loves magnetite. So when magnetite crystallizes, the vanadium-scandium ratio decreases. In a high pressure melt, hornblende crystallizes before magnetite, and hornblende takes up scandium, but not so much vanadium. So the ratio goes the opposite way. Right, so these are the common fractionation indicators we're going to look for in Hugh Smithy's new database of Yilgarn granites. There's one more thing here. This is a zirconium-hafnium ratio. So the crustal average zirconium-hafnium ratio is 36:1. Once we get to about 70% SiO2, then zircons start to crystallize and fractionate, and the effect of that is to lower that ratio. So if I just plot hafnium against zirconium, we can see most of these things plotting around 36:1, and in silica-rich magmas, you can see this ratio decreasing. We'll quickly have a look at the difference between alkaline and calc-alkaline magmas. The way this was originally defined way back in the 1930s, if you consider calcium, sodium, potassium, and aluminium, almost all of those elements are accommodated in feldspars. Right? And calcium-rich plagioclase will crystallize first, and as the silica content increases, the plagioclase becomes less calcic. So with fractionation, calcium goes down, but sodium and potassium will go up. And there's a crossover point in here. So the guy who originally defined alkalic magmas said, if the crossover point between calcium and sodium plus potassium occurs at less than 51% SiO2, then we'll call those things alkalic magmas. And that's a bit messy, so we don't bother plotting the calcium anymore. Now we just plot diagrams like this. We'll just look at sodium plus sodium plus potassium. So this is Hughes data from the Barcode project plotted on one of these alkali plots. And these points in here are actually pretty close to the red line on this, right? So if we had things that were more than 6 or 7% sodium plus potassium at 60% SiO2, then we would start to call these things alkalic. Here's a really interesting thing about alkalic magmas. In this plot, I've taken Hughes data from Kalgoorlie and I've plotted all of the low thorium basalts. So these are things that have chemistry like London basalt. Right, so this is the green data, and you can see the vanadium-scandium ratio averaging about 7 in accordance with the prophecy. These are basalts, tertiary basalts from Tasmania. These are alkalic basalts, right? So everybody who's ever worked on porphyry systems said the vanadium-scandium ratio tells you something about hornblende fractionation. Well, normally that's true, but it isn't always. With a low degree of partial melting, and that's what alkalic magmas are. Alkalic magmas represent a very low degree of partial melting. So if we have some kind of basaltic source region that's being melted, with a low degree of partial melting, the oxides melt before the silicates. So that means these magmas are depleted in scandium because most of the scandium resides in pyroxenes or amphiboles if there's any amphibole present. So if we melt all of the oxides before the iron silicates, then it generates a magma that has a really high vanadium-scandium ratio. And these are really oxidized magmas. We are melting all the things that contain Fe3 plus before the things that contain Fe2 plus, right? So alkalic magmas are almost always really, really oxidized. And because it's a low degree of partial melting, it will melt all the weird things first. So it melts all the phosphates, all the oxides, and the zircons before it melts pyroxenes and plagioclase. It'll melt the alkali feldspars, so they'll have lots of potassium, lots of sodium, lots of barium, lots of strontium. And another weird thing, I don't quite know why this is, but alkalic magmas have really, really high zirconium to hafnium ratios. So these things are really high zirconium, but a really high ratio. And that's a distinctive characteristic of strongly alkalic magmas. Right, so this has got nothing to do with mineralisation. These are just common garden variety alkalic basalts that are typical of any of the tertiary volcanoes in Eastern Australia. And it turns out that the Proterozoic dikes that crisscross the Yilgarn are like this as well. That's why they're magnetic. Now we'll do the same for Wallaby. The pink dots in here are the Wallaby cyanites or the alkalic intrusions. They're not all cyanites. And the pale blue things are the Wallaby conglomerate. So you can see this crazy high vanadium-scandium ratio in the cyanites, and you can see the crazy high zirconium-hafnium ratio. Right, really distinctive characteristics of alkalic magmas that you can easily see without looking at elements that move around during hydrothermal alteration. Now we'll go and look at Hughes' analyses of the granites, and these are coloured by the classifications that were originally made by Kevin Cassidy and Dave Champion. So they classified things as mafic granites. So these are high pressure melts, high pressure hydrous melts from a basaltic source. So they've got mafic granites. The low calcium granites are mid-crustal melts. The high calcium granites are kind of somewhere in between. And the things they classified as high field strength enriched granites are sometimes part of the low calcium suite, but sometimes alkalic. So either process, like a high degree of fractionation or a low degree of partial melting, will both generate magmas that are strongly enriched in high field strength elements. Normally I'd use these diagrams just for alteration, but these are rocks that are not altered. So in this case, it shows you how these things progress from sodium and calcium rich in the high pressure magmas, where plagioclase has not fractionated, into much more potassic granite, where the plagioclase has fractionated. Right, so you can see that trend from high sodium, high calcium to high potassium. And then you can see the syenites plotting out here near this tie line between orthoclase and albite. Now let's go and look at the fractionation diagrams we were just considering before. If we look at the strontium-yttrium ratio, you can see that strontium-yttrium ratio is going higher and higher and higher through these mafic series granites. And you can see that there is no europium anomaly. So these are magmas that have not fractionated plagioclase, but they have fractionated titanite. And titanite is sucking all the yttrium out of the melt. Now, this is a signature of high pressure hydrous melting, whereas the low calcium granites are depleted in strontium, but enriched in yttrium. You can see that most of these have a zirconium-hafnium ratio around 35 to 40, but these ones up here with ratios higher than 40, they are getting really interesting. And you can see most of the vanadium-scandium ratios in the high pressure magmas are around 7, 8, 9, 10, with a few higher ones. So these things in here are likely to be highly fractionated. Either they've fractionated a lot of hornblende, or they are alkalic magmas with a low degree of partial melting. I'll skip through these quickly because it's same. In the high pressure magmas, you see that the niobium content goes down. That's titanite fractionation. And the yttrium content goes down. In the low pressure melts, the niobium and the yttrium are highly enriched, and thorium is highly enriched. Right, so we're comparing and contrasting compatible versus incompatible behavior of the high field strength elements due to titanite fractionation. I'll skip that. Right, so what I've done now is I have plotted all of those same data points in the small grey points here. Right, that's the background. And what I've done is I've gone to Hughes database, or I've gone to published sources of analyses of granites from a few mineralized localities. These would look better if I plotted the whole data cloud rather than a single point. But for each of those mineralized intrusions in these gold camps, I've taken the median composition of those particular intrusions. And you can see that most of these have really high strontium-yttrium ratios. Alkalic magmas don't always have high strontium-yttrium because they're often highly enriched in yttrium, but they'll always have really, really high strontium. You can see some of these have got crazy high vanadium-scandium ratios. None of them have fractionated plagioclase, and most of them have really high zirconium-hafnium ratios. So that's a really distinctive alkalic signature. The odd ones in here are the hornblende diorites at St Ives and at the Golden Mile. The things at St Ives and the Golden Mile have chemistry that is much more like porphyry copper magmas. Like these are just bog standard hornblende diorites, high pressure hydrous melts. And the one geological thing that's different about St Ives to the Golden Mile is it's the one place where we see a large amount of crustal contamination in the earlier tholeiitic basalts. And I suspect there's some kind of common indicator, some kind of common process that links that. This is all about how do we get sulfur enrichment in the mantle source. So that's the end of all the heavy-duty theory. Alicia wanted me to make some comments about how do we put all this stuff into practice. So I'm going to put some practicality in here. If you're out on the rig or in the core shed logging porphyries, the best thing you can do when you're logging porphyries is to log the phenocrysts. You should be logging which minerals are present as phenocryst phases. So it's going to be feldspar, amphibole, quartz, and sometimes biotite. So you should log which minerals, how much, what's the proportion, like 5, 10, 20%, and how big are they. Don't correlate your logging based on alteration or colour. So here's an example. Here's a really, really crowded porphyry, but it's very fine grained. So this has got masses and masses of fine plagioclase phenocrysts and tiny little hornblende phenocrysts. This is the same rock, 3 different styles of alteration, but the texture, the abundance, and the types of phenocrysts are exactly the same in all of those, right? That's all the same rock. Here's 3 porphyries that visually look similar, but are different. So this one is a crowded porphyry. It's got lots of big plagioclase. It's got some little white K-spar. It's got a few little hornblende crystals in here that are all altered to biotite. And it looks similar to this one, except this one has got quartzite in it. Right? And mineralogically, this one looks like this one. This has quartzite as well. But look at the difference in grain size. Right? So when you're out on the rig, just log what minerals are present as phenocrysts, what are the proportions, what's the size. Don't worry about the colour or the alteration. Log that as well, but don't use colour or alteration to correlate from hole to hole. This is what you really should be doing. When you're drilling a prospect, it's especially important on the first diamond drill hole. On your first diamond drill hole, go and get good quality multi-element chemistry and plot it as strip logs. So in this case, I have classified the rock types partly from logging and partly from chemistry. And look at this. If you look at scandium, you can see a distinct break. Right? If we plot this as a strip log, here's a distinct step in the scandium content. That's got to be a contact. That's got to be a contact. That's a contact. There's a few little mafic things in here where the scandium jumps up, but you can see where the contacts are by plotting the strip logs in the chemistry. So when you see that break in the immobile trace elements, go back to the drill core and make sure you can find the contact. And then make sure you can identify visually what this rock is. So make yourself a rock board with type examples of this unit, of this unit, of this. So when you get more drill holes or more drill chips, you can use that rock board to inform your logging. Right? If you calibrate your logging by using good chemistry first, then you'll be able to correlate much more accurately from hole to hole. Now I'm going to show you one tiny little case study from Burns. So Wade Johnson, he's a really good bloke. He sent me his multi-element geochemistry from his first few diamond drill holes. And we did exactly that kind of process. So I haven't correlated this exactly against core photos or drill core in person. But when we plotted it up, we could see vanadium-scandium ratio here. And we've got a group of things in here that have a high vanadium-scandium ratio. So these are magmas that have crystallized and fractionated hornblende before they crystallize magnetite. Right, so these are high-pressure hydrous magmas. And when we plot a strontium-yttrium ratio, we can see all of these things in here split out into 4 different groups. So we've got these red ones in here, which look like stock standard hornblende diorites. We've got this yellow group, which is really high in strontium, but much higher in yttrium. And we've got this magenta group, which is crazy high values in yttrium. Right? It's really part of this suite, but these ones are really alkalic. And then if I plot some of the high field strength elements, these ones with the higher yttrium have got much higher thorium as well. So these things have not fractionated titanite. So the yttrium and the thorium are not coming down. These are likely to be a low degree of partial melting. These are seriously alkalic magmas. And when you look at the grade, this is one little dike, right? But these things have got much higher copper and gold than any of these other things. So as these things are becoming more and more and more alkalic, the grade is getting higher and higher and higher. And with chemistry like this, we can correlate from hole to hole and section to section and join up a series of parallel dikes from this evolving magma suite. So that's how we should be using this kind of data for the field geos for the guys on the rigs, right? You'll get a much better geological interpretation if you can use the chemistry to calibrate your logging. I want to make one quick comment about the geochronology. You would have seen heaps of Trippy's presentations before, so you'll know that we've got a sequence from London basalt to low thorium basalts to high thorium basalts to black flag beds, and then an unconformity, and then we'll go conglomerates to sandstones. So we'll see lots of those high pressure hydrous magmas that form hornblende diorites intruding into these greenstones. And when we go and date the youngest of those, they'll generally come back about 2665. Whenever we see intrusions that are in place into the epiclastic basins, every one of them I know of that's this younger suite are all alkalic, right? So there's and the time break is not very much. The time break between the last of these things and all the alkalic magmas, from what we can tell in the geochronology, may be just 3 or 4 million years. But every intrusion into the late basins that I know of is alkalic. So the really important question here is, how do we get gold enrichment in a mantle source? And I'm pretty sure it's about having immiscible sulfides present in the mantle at an earlier stage of that evolution. So the two ways we might get immiscible sulfides in the mantle is if there was a batch of magma that was trapped in the mantle, like it didn't get emplaced into the upper crust. It cooled down, crystallized hornblende, then started crystallizing magnetite and became sulfide saturated. Now, if there's some kind of magmatic replenishment or another injection of mafic magma that remelts that, that's how we're going to generate alkalic magmas. So I think alkalic magmas pick up their sulfide load by remelting earlier magmas. There's lots of alkalic magmas in the Yilgarn, there's a relatively small percentage of them are mineralised. But the vast majority of things that are mineralised are alkalic. Now, the exception to that, as I said, is St Ives to the Golden Mile, and that's the one place where we see a lot of evidence of crustal assimilation in the basalts. So it might be that that part of the crust has had sulfur added via crustal assimilation. And that's purely speculation there, but hopefully from this you can see there's really simple discriminants you can use to tell the difference between those high pressure hydrous magmas and the low pressure mid-crustal melts, and then to pick the alkalic things. The alkalic things are the really, really interesting ones. That's it, I'm done. Everybody asleep?